Somewhere in spacetime, there's a gate that spits everything out and admits nothing. That gate has a name, a white hole. Here's the quick payoff: it's the time reverse of a black hole. Outside, gravity feels identical and the shape looks familiar. But the horizon is an exit, so nothing can go in. Light and matter only leave, because geometry pushes every path outward. Einstein's math permits this odd twin cleanly, without tricks. Nature resists it, yet the idea sharpens what time and gravity mean. You aim a flashlight at a brilliant sphere, and nothing enters. The beam touches the boundary, then peels away like water on glass. That picture captures the white hole idea in plain words. A white hole is the time-reversed version of a black hole. This matters because time reversal flips causal arrows at the horizon. If black holes trap, white holes expel, so trajectories run outward. Spacetime tells matter where to go, and it refuses entry. The exterior field matches a black hole perfectly, at equal mass. Only the allowed directions at the horizon change their sign. Here is how the geometry enforces that behavior cleanly. Geodesics are the straightest paths through curved spacetime. Near a white hole, those paths tip outward, even for light. Infalling options vanish from the menu because causal structure forbids them. No rocket can override that because geometry beats thrust. Example in real terms, try orbiting just above the horizon. For a one solar mass object, that horizon sits near 3 kilometers. Your path decays outward, like a fountain stream pushed by pressure. Fire your engines at full throttle, and you still drift away. Chase photons inward, and they boomerang back with a nasty blue shift. Drop particles from far away, and they never cross the surface. They skim, accelerate, then slingshot toward cosmic distances. So the picture is simple. White holes look ordinary from afar, yet act like outward-only valves. Now the wild part arrives straight from Einstein's field equations. The Schwarzschild solution describes a non-rotating spherical mass exactly. Extend it maximally in time, and extra regions appear. One region looks like a white hole, the mirrored time cousin. That construction matters because it shows clean consistency within relativity. We are not hand-waving monsters here, the equations allow it. The full causal diagram includes a black hole, a white hole, and 2 distant infinities. A bridge briefly links the black and white sides in the math. People call that bridge an Einstein-Rosen bridge, a kind of wormhole. It pinches too quickly for travel, so crossings fail. The white region exists in the solution, not as a formed object. It needs impossible initial conditions stretched across the infinite past. Example you can visualize: take a Penrose diagram with tidy rails. Light rays lean at 45 degrees on the grid. The white triangle funnels everything outward, always and everywhere. Send any signal inward there and the diagram denies it. That denial is causal, not technical, because geometry sets the rules. So the picture is simple. The equations allow white holes, but forming one is another story. Real space is noisy, and small disturbances grow near horizons. White hole horizons are hypersensitive to tiny incoming ripples. That sensitivity matters because nature rarely offers perfect stillness. A stray photon nudges the future, and chaos answers loudly. Here is the mechanism in straight words, without suspense. Infalling waves reflect and amplify at the horizon, gaining energy. Each bounce blue shifts the wave, boosting frequency and punch. The growth can be exponential with modest, persistent perturbations. Eventually, the exit surface cannot remain a clean one-way gate. The ideal white hole collapses into something more ordinary. Tiny tests toss a single particle toward the boundary. It never crosses, yet its field still perturbs the geometry. Add dust, starlight, or tidal rumble, and amplification avalanches. The compound mess seeds a trapped region that resembles a black hole. Several analyses show the white region is linearly unstable. It needs a conspiracy of cancellations that the universe withholds. Example with a number that sets the scale. Double the energy with each reflection for 10 quick bounces. The factor reaches about 1,000, which wrecks the structure fast. Bottom line, real white holes shred themselves under the slightest touch. Thermodynamics puts another arrow into the heart of white holes. Black holes radiate slowly, with temperature set by surface gravity. A solar mass black hole sits near 60 nanokelvin in temperature. Reverse time, and you need an exquisitely tuned incoming bath. That bath must cancel every outgoing quantum trajectory with precision. This matters because entropy prefers disorder over surgical cancellation. White holes demand the opposite trend, so disorder must unwind. How would that feel at the level of heat and quanta? Outgoing radiation would seem to leap back into narrow lines. Every mode must grab the right phase and run backward. That alignment is statistically microscopic and painfully rare. Rule of thumb, unlikely microstates never power massive astrophysical engines. Example, in real life, air spreads across a room naturally. It never rushes to one corner, then organizes your desk. A white hole needs that kind of miracle for fields. If one appeared, it might look colder than its surroundings. It would absorb precisely the quanta that happened to arrive. It would act anti-thermodynamic, like a refrigerator run by coincidence. Net result, the thermodynamic arrow leans hard against living white holes. Quantum gravity could cheat the story near crushing cores. Several approaches replace singularities with short, explosive bounces. That idea matters because it avoids truly infinite densities. A collapsing star could look black outside, then rebound inside. The rebound might later erupt as a small white hole remnant. Mechanically, quantum pressure halts collapse near Planck-dense conditions. The trapped region stores energy, then tunnels into an expanding phase. Outside clocks tick slowly there so eons can pass invisibly. Inside clocks differ, and the bounce completes in moments. When the tunnel opens, the horizon flips its causal direction. The outburst vents mass and radiation in a brief flash. Example numbers are uncertain, so treat them as sketches. An asteroid mass remnant could release a millisecond burst. A solar mass remnant might wait longer than the universe's age. Observers would see a compact transient with a sharp profile. No accretion afterglow should follow, which helps identification. So the picture is tentative. Quantum bounces offer a pathway, not proof. We can still hunt by asking what a white burst mimics. Fast radio bursts are quick, bright, and puzzling in origin. That connection matters because their timescales match some bounce sketches. If a remnant vents fast, a radio flash could follow. We can check energy budgets against plausible mass scales. FRB energies cluster between 10 to the 31 and 10 to the 33 joules. A tiny remnant could cover that without breaking known limits. Gamma-ray bursts are also impulsive, with fierce high-energy profiles. Most of them show afterglows from jets and accretion. A white hole outburst should lack extended accretion afterglow entirely. Survey catalogs help by filtering fast, isolated, repeating events. Another angle considers primordial remnants as a dark matter slice. If many existed, their occasional bursts would pepper the sky. Non-detections place limits on how many can hide comfortably. Instruments improve yearly, tightening bounds with patient statistics. Example survey math is simple at heart and useful. No events above threshold across n hours gives a rate ceiling. That rate becomes a density limit given a brightness model. What to remember, observations have not revealed a clear white hole signature. Big ideas invite metaphors, and white holes attract bold ones. People often ask whether the Big Bang was a white hole. The crisp answer says the comparison is poetic, not literal. The early universe expanded everywhere at once, not from a point. There was no outside to eject from, so the analogy breaks. That matters because words can sneak in wrong pictures quickly. Another favorite suggests travel through wormholes with white hole exits. In the exact Schwarzschild bridge, the passage pinches too quickly. Exotic matter does not easily hold such throats open. Quantum inequalities throttle how much negative energy can help. Mechanically, you cannot steer into a white region from outside. You could only arrive if the entire spacetime began that way. Example to settle intuition, imagine a waterfall you cannot enter. Water always flows out and the stone face blocks swimmers. That is the white hole story as a causal barrier. Bottom line, these comparisons sharpen intuition while trimming the myths. That gate that spits everything out and admits nothing remains mostly math. The equations allow it cleanly, but nature seems allergic to it. Instability and entropy both lean hard against seeing one alive. Still, the hunt teaches how time and gravity braid together. If this sharpened your picture of horizons, that was the win. I will keep chasing the sharpest space mysteries with calm explanations. Subscribe if you want more cosmic clarity without the fluff.